We want to design a system that will allow people to pay each other without trusting a third party. With a third party, whether it is a bank, Venmo, PayPal, or any other financial institution, you are trusting that they will reliably make your payment to the other party in an acceptable amount of time. If they are experiencing any issues or downtime, there is nothing you can do about it. They also know all the transactions that you make since they own and store that data. Let's see if we can design a system where people can pay each other without relying on a trusted third party. Let's look at a currency that uses trusted transactions, but instead of trusting a single entity like a bank, people trust transactions because they're verified by everyone who uses the currency. Imagine Bob and his friends are starting a new payment system to pay each other called FriendCoin. Instead of using anything physical to represent the currency, like coins or paper, each person maintains a record of who owns what and all the transactions that have occurred. They all decide to start with 10 FriendCoin. The first transactions in the history are the creation of everyone's FriendCoin. FriendCoin creation is just a special transaction where a person's amount of FriendCoin is increased. Suppose Mary and Joe want to transfer some FriendCoin between them. Mary, being the sender, tells everyone, "Hey, I want to send 4 FriendCoin to Joe." Everyone first checks if Mary has 4 FriendCoin available to send. They then write down the transaction and update the amount of FriendCoin that Mary and Joe owe. Then they tell each other about the validated transaction so that everyone agrees on how much FriendCoin Mary and Joe have, and also the transaction history. Joe now has 14 FriendCoin and Mary has 6. Note that nothing was actually transferred between Mary and Joe. Mary told everyone how much she wanted to transfer and who to transfer to. Everyone else validated and agreed with the transaction, resulting in Joe having 4 more FriendCoin. He can use his new FriendCoin amount with any of his friends, since they all agreed and acknowledged that he has 14 FriendCoin. Let's look at another transaction. Joe wants to transfer his 14 FriendCoin to Lisa. He tells everyone else, "I want to send 14 FriendCoin to Lisa." Everyone checks their records and sees that Joe has 14 FriendCoin to send. They record the transaction along with Joe and Lisa's new FriendCoin amounts. They tell everyone else about the transaction to make sure everyone agrees. Once agreed upon, Lisa has 24 FriendCoin and Joe has 0. Note that with this transaction, like the previous one, nothing was actually transferred directly between Joe and Lisa. Joe told everyone about the transaction, and others in the group validated and agreed upon the transaction. The transaction history and record of how much FriendCoin each person owns, which each person in the group has a copy of, is the source of truth for what any of the friends can spend. FriendCoin is very similar to Bitcoin. Imagine all the people using FriendCoin as computers sending messages about transactions to one another. Each computer maintains its own record of who owns what in the transaction history. In the terminology of Bitcoin, every computer on the network shown here is known as a node. When 2 people pay each other, the transaction gets sent from the sender's computer to the computers it knows on the network. Unlike the one pictured here, Bitcoin is a big network, and computers aren't aware of every node on the network. The transaction is sent around until all the computers have received it. In this network, all the computers communicate with each other with the same types of messages, like transactions and verified transactions. We call this a peer-to-peer network. All these computers interact with all the other computers in the network, and no computer has a higher privilege than the others. In this network, the state, which is the transaction history and a record of who owns what, is maintained by each node on the network. Each node communicates with the others to come to an agreement on the state. This is called a decentralized network, since the state isn't in one central place. The state is referred to by some people as a decentralized ledger, which just means a record of financial accounts that is not stored in a single place, as shown here. Just like in FriendCoin, if each computer on the Bitcoin network has a transaction history and record that show you own some Bitcoin, you can spend the Bitcoin on the network. That is what Bitcoin is. It is simply an entry on a decentralized ledger stored by every computer on the Bitcoin network. Let's go over how our current network works one more time. A transaction is proposed and sent to the network. Nodes validate this transaction, add it to their history, and send this validated transaction throughout the network to ensure everyone has received it and has added this transaction to their copy of the history. there are some problems with this network. How are funds secured to one person? Could someone propose a transaction spending another person's money? A transaction gets proposed, those on the network validate it, and then broadcast it. This works when a few transactions are being proposed, but if many transactions get proposed, then the network can get potentially overloaded. If someone proposes one transaction and then another, with the two transactions spending more money than the person has, which transaction should the nodes verify and accept? Some nodes may receive one transaction, and some may receive another. You need to be able to enforce some ordering of transactions.
Is the transaction history tamper-proof? Could someone just change the transaction history and also change the amount that someone owns? In the next lessons, we'll see how Bitcoin solves all these problems.
In order for people to use computers to send and receive money, we need some kind of identity system that can be used and recognized across all computers. Usually in your country, you have public information like your name, address, telephone number, and you have private information that you can use to verify your identity, like a social security number. You must keep the private information secret, or someone could use it to steal your identity. In Bitcoin, the public information is called a public key, and the private information that you must keep secret is called a private key. The private key is just a randomly selected number. Here is an example of a private key. You might be like, what? That's a number? With normal digits, the number would be 78 digits long, so we use a different number system here which uses numbers and letters, called hexadecimal. The public key is just another number that is generated from the private key by putting it through a series of complex mathematical transformations, such that there is no way you can find the private key from the public key, other than guessing. But since the public key was generated from the private key, they have a mathematical relationship, and we will later see that we can leverage that relationship for securing Bitcoin. The private key and public key together are called a cryptographic key pair. Cryptography is the practice and study of communicating securely in the presence of adversaries. In other words, being able to communicate on open channels such as the internet, where people could intercept your messages and monitor what you're sending, but having that communication still be secure. Bitcoin makes heavy use of cryptography since it is a protocol for making secure payments over the internet. Hence, it is referred to as a cryptocurrency. How exactly do we generate this key pair? There are many tools to generate these keys, as the algorithms used for generating the keys are used for many other computer applications. This tool here is called OpenSSL, which is free and available for anyone to use, but this doesn't look easy to use, so key pair generation is usually taken care of by wallet software. You've probably heard that you store your Bitcoin in wallets. Well, this is a misconception. You store your private key within your wallet so that no one can forge your identity and spend your funds. We will see how identities and the actual amounts of Bitcoin are interconnected later on. You can generate as many key pairs as you want to use on the Bitcoin network, which means an unlimited number of identities. Here we see the page of the Trezor wallet, where key pairs are generated. Note that it says address rather than key pair. A Bitcoin address is simply a shortened version of a public key. The private key isn't revealed to you because the wallet is making sure it is stored securely to avoid any user error resulting in the private key getting lost. If anyone has your private key, they can spend your Bitcoin, as we will see later on. To generate new key pairs, all I need to do is click the More Addresses button, and I get more addresses available to use. Bitcoin was made to support a higher level of privacy than a conventional payment system, where you use the same payment details every time, creating a paper trail tied to your identity. In Bitcoin, you can generate as many key pairs as you want, giving you multiple identities and making it harder to track your transactions and payments. Now that all the computers have key pairs to use as identities, how can they use these to transmit payments and secure their funds? To solve this, we present the digital signature. You can think of a digital signature as a special stamp. You use the private key to make an invisible stamp on some data. Think of the public key as a magnifying glass that you can use to see the invisible stamp. If the data that was stamped is modified or tampered with in any way, or if someone used the wrong private key, the stamp shows up as red. If not, the stamp will show up as green, looking through the magnifying glass. A digital signature works the same way. You take some data, you take your private key, and you produce a signature using the digital signature output. Then someone can take the data, the signature you produced, and your public key, and verify that the signature came from your private key. In Bitcoin, when someone has paid you, they specify an amount of Bitcoin, and they also specify a condition that needs to be met to spend the Bitcoin. This condition usually involves a digital signature of some data. The condition states, I need a signature by the person who has the private key matching this public key. This means they have addressed the payment using the public information of the recipient, which is their address. The recipient will need to use their private information to prove their identity in order to spend it. As long as the individual with the private key has stored it securely, they can generate a signature on the data and provide that signature as a part of a transaction where they spend that Bitcoin. When the transaction is validated by the other nodes in the network, they will check the signature and verify that it is valid. If the signature is invalid, the transaction will be rejected. This is why it is essential to store your private key securely. If someone is able to steal your private key, they can create valid digital signatures and spend your Bitcoin. Let's look closer at what goes into a Bitcoin transaction. Bitcoin transactions consist of inputs and outputs. The funds you have available are the outputs of previous transactions. Outputs of transactions that haven't been spent yet are called unspent transaction outputs, or UTXO for short. Suppose you wanted to pay someone 50 Bitcoin. You find the output of a previous transaction which was paid to one of your addresses, which has at least 50 Bitcoin. You reference the transaction which contains this output by using its identifier, and provide the digital signature using the private key of the key pair that allows you to spend the output. The digital signature is called the unlocking script, shown by the field script sig here. Your output will contain an amount and a condition that needs to be satisfied to spend it. This condition is called a locking script, which will require the recipient to provide an unlocking script to spend this output in a transaction, just like you did for your input in this transaction. The transaction is then encoded and transmitted to the network. Another aspect of transactions is that outputs must be fully exhausted in the transaction. If you were to pay for a $7 sandwich with $20 in cash, the cashier would accept your $20 bill and hand you back $13. Bitcoin transactions must have change as well. Here we see an output of about 1 Bitcoin used. About 0.3 Bitcoin is sent to one address, and the remaining Bitcoin is sent to another address owned by the user. After seeing those examples, you are probably like, wow, making a Bitcoin transaction is so complicated. Luckily, your wallet software will take care of most of the hard work for you. The wallet software keeps track of the Bitcoin you have received for all of your addresses. As you can see here, the wallet allows you to create accounts, which are groupings of addresses. The wallet will then tell you all of the Bitcoin you have received for those addresses. All you will have to do to send Bitcoin is specify an address of a recipient and the amount. The wallet will construct the transaction, including the inputs, the outputs, and the required digital signatures to spend your Bitcoin. It will then take that transaction and broadcast it on the Bitcoin network. To recap what we learned in this lesson, computers use cryptographic key pairs as identities. They have two parts, a public key and a private key. The public key is public information that can be shared with others on the network, and the private key is secret information. Key pairs are generated and stored by wallet software. Private keys must be kept secret as they are the most critical part of proving your identity on the network. When spending Bitcoin, you prove your ownership by creating a digital signature on some data using your private key. You include this digital signature with your transaction, and this signature will be verified by all of the other nodes on the network using your public key. We've seen how identities work in Bitcoin and how Bitcoin amounts are secured by cryptographic key pairs. Let's go back to a bigger view of the network. All nodes on the network need to agree on what the transaction history is by following the same rules for validating transactions and adding them to the transaction history. Let's see how this process works. Let us first introduce a key component of this, a hash function. A hash function takes in some input and the output is some random fixed size data called a hash. The key property of a hash function is the hash for a particular input will never match the hash of any other output. You can think of the output of a hash function as the DNA of an input. The DNA of a person does not match any other person's. Similarly, the hash of some data will never match the hash of any other data. Another important property of a hash function is it always produces a hash of the same size. So regardless if you put ABC or a document with 10,000 characters into the hash function, it will always give you a result of the same size. Hashes are also randomized, so you have no idea what the hash of an input is without actually putting it through the hash function. If you looked at a person, there was no way you could guess what their DNA was. Same goes for the hash of some data. You'll never know what the hash will be for a certain input until you actually put it through the hash function. We need a way of determining the correct transaction history that each node can use independently. Right now, we receive transactions that have been validated by other nodes on the network. How can we order these transactions? Attaching a time to each message wouldn't work because Bitcoin is used on computers all across the world, which all have different clock times. We can instead use the ID of the transaction. The ID of the transaction is simply the hash of the entire transaction. And since hashes are unique, each transaction will have a unique identifier. Assume all nodes start with the same transaction as the start of their transaction history. For each transaction that is proposed, we can include the ID of the previous transaction that it follows. This effectively creates a chain of transactions, with each new transaction referencing the previous one using its identifier. Imagine someone has some Bitcoin they want to spend. What happens if they send two transactions at once, spending that same Bitcoin and sending it to two different people? They are trying to spend some Bitcoin multiple times. Some nodes will receive one transaction first, and others will receive the other. So different nodes will verify either of the transactions, and then send those verified transactions all over the network. Some nodes will receive one transaction and extend their current chain with it, while others will extend their current chain with the other transaction. Nodes will eventually receive both transactions that have been verified, so they will have to create an additional chain since both transactions have the same previous transaction identifier. For the transactions after, nodes might want to extend either of the chains. Eventually, one of them will be longer and become the official transaction history. Thus, the transaction in the shorter chain won't be valid. Nodes treat the longest chain as the official transaction history and will always try to extend the longest chain first before creating a side chain. We still have some issues here. Say someone wants to rewrite the transaction history. They can generate a bunch of transactions they have verified themselves, forming a chain that's longer than the current longest chain. Then they can send these transactions out all at once, which will then become the transaction history for the network, since the other nodes will accept this additional chain. We need to make it hard to rewrite the transaction history. To do this, we will introduce some work for the nodes to do in order to propose verified transactions to add to the history. When Bitcoin nodes propose transactions, they include some other data. This data includes the hash of the previous link in the transaction chain, a date and time, a target, a nonce, and some other things. We will explain what the target and nonce are shortly. This data is known as a block header, and together with the transaction data, the entire structure is known as a block. The chain of transactions that form the transaction history discussed earlier is actually a chain of blocks, which are linked the same way by storing the hash of the previous block's header within the current block's header. This is Bitcoin's transaction history, known as the blockchain, and is stored on every node on the Bitcoin network. So what work will the node need to do in order to propose a block? It has to be something that can't be cheated, and it needs to consume a significant amount of some resource, so that people proposing blocks can't take over the network unless they have massive amounts of that resource. In Bitcoin, the resources that are consumed by people trying to propose blocks are computer processing power and electricity. We will make anyone who wants to propose a block make sure that their block header's hash is under a certain number called the target. This means taking the block header, getting its hash, and seeing if it's under the target. If not, the data must be adjusted and attempted again. Since any unique data will have a unique hash, the block header has a nonce, which is simply a number that can be increased or decreased to make the overall data different. The header also has a date and time that can change by seconds or minutes to cause the data to be different as well. It may be confusing that this entire structure goes through the hash and comes out as a number, but computers really see everything as numbers, so your computer sees the entire block header as a number, which means a number goes into the hash function and the resulting output is a number as well. Since hashes are random and you have no idea what the hash will be for some data, you just have to keep hashing the block header with minor adjustments until it is under the target. This process is known as mining. It is basically a big guessing game. You can think of it as playing a slot machine until you hit a jackpot. Computers are continuously playing this guessing game, which causes them to use electricity since they have to be on and operating at a high level until they find a valid hash. Computer processors have a limit on how many hashes they can do per second, so people have started to use higher performance computer chips so that they can guess more hashes per second in order to find a valid block. These higher power performance computer chips are expensive and need more electricity to operate, thus the success a miner has is dependent on how much he pays for electricity and how fast his computer hardware can mine. Miners are competing against each other to mine blocks. Once a block is found, it is broadcasted on the network. When other miners receive a block which has the same previous block ID that they were mining the next block for, they validate and add this to their blockchain and begin trying to mine the next block. Every block in the blockchain has been mined by a miner on the network at some point in time. This means the collective computing power and electricity of all the miners has been used to find all the blocks in the blockchain, and is why the longest chain is regarded as the valid transaction history, since the majority of the network decided to put their computing power and electricity into finding the blocks in that particular blockchain. Miners control the transaction history by proposing